electric potential has a very specific definition, and it's an important idea in physics because all of modern life is harnessing the fact that inside an electric field, you can store up electric potential. You can store up energy, okay? And all of modern life is, we need this, okay? We need juice, we need power to run your phone, your GPS. And in the future, this is what's going to make all our cars go, an electric car. It's totally the future. Because really, burning gas, it's so old. It's old school. But we got to figure something out fast. And battery technology, that's huge. Okay? I don't know if you heard on the news, but recently they're trying to make Michigan, hopefully we can get contracts for the new battery capital of the world. If we can have super awesome battery technology, this is what's going to drive the future. Not only for computers and stuff, but for cars. That's really the future right there, if we can get this figured out. But anyway, electric potential. The symbol for electric potential is this, triangle V. You guys familiar with this triangle? It is a Greek letter delta. That's correct. Okay? If you go visit a college, you might see like different fraternities, sororities, Delta, Kappa, Sigma Phi, whatever. Okay? Delta is a Greek letter that in science we use for change in. Okay? So the change in voltage, or electric potential, is defined as the change in PE, potential energy, per quantity of charge in coulombs. Okay? So what the heck does that mean? This is so abstract. Okay? You're not used to the idea of electric potential, but you've all heard of volts and voltage. Where do you hear volts and voltage all the time? Talking about batteries. Okay? So you know when you're checking your cell phone or your iPod or whatever to see how much juice you got left? All that is your cell phone or your iPod's got a circuit to measure the voltage, okay, to see how much juice you got left. Same thing with your laptop, etc. Okay? So let's unpack this a little bit. And sometimes to make this equation easier, we drop out the delta because we assume that, of course, it's a change in your potential, right? To not make it so cumbersome there. So two analogies to make this easier. One is the height of an electric hill, and the other is water pressure. Okay, so you're like, what are you talking about, Mr. Lau? I don't get it. So first analogy is height on a hill. This is an awesome, awesome old school toy. Brings back many happy memories from Mr. Lau's childhood. Yay. Okay? Actually, no, I didn't have one of these when I was a kid. So part of physics is reclaiming your lost childhood. By the way, bonus, I'm always looking for old school toys like one of these. If you're cleaning out, like, you know, your uncle or your grandparents' house and you see one of these, don't pitch it. Donate it to the physics department. I'll give you a little bonus, okay? Anyway, ironically, how does this toy work? It's actually powered by a battery. That's so ironic. What's the job of the battery? To provide electrical energy. You see that? To a motor. What does the motor do? It runs this really annoying squeaky escalator. And these are little tiny seals that go up this electric hill. You see that? And then when it gets to the top of the hill, is that energy lost or is it stored? It's stored up against gravity. That's called potential energy, specifically gravitational potential energy. Then that energy is released as the seals flow down the hill, assuming there's not too much friction, even though these wheels are older than you are. And then it goes back to the bottom of the hill. The process repeats itself. Think of this as a battery, except a battery, instead of moving tiny seals around, these are like electrons. It pumps it up an electric hill so that the charges can flow and power the screen on your iPhone, your wireless internet, a text message, you name it. You see that? All of modern life is because we can take a charge from here and move it to there. Yay. And we can store it up. Life is good. It's all about the juice, right? Juice, baby. There we go. But not Jamba Juice. We're talking electrical juice. Got it? Okay? I don't get it. So an analogy is electric potential is like how high you go up, an elevator or a mountain. Okay? So think about it. When you go skiing or snowboarding, I forgot. Skiing is like for old people. There we go. Just kidding. Okay? Where do you want to go snowboarding? Like in Chicago or like Colorado? Yeah, right? You want to go to like Vail, right? Or Whistler up in Canada. Because there you got mountains. And the first thing you do is you go up a ski lift, right? Or a chairlift. The job of the chairlift is actually to give you energy. That's what it does. It takes you to the top of the mountain, right? When you go up to the top of a mountain, it takes a lot of energy to run that ski lift, doesn't it? And that energy is not lost. It's literally stored in your body against gravity. And then as you go down that mountain or that hill, you release that energy. You see that? Very exciting. Are you excited? Pretend you're excited. There we go. Next analogy, water pressure. We're talking toilets. Huh? Here we go. If you think about it, it's a very simple idea. Water always flows from a point of high pressure to low pressure, right? From a point of higher pressure to lower pressure. So in every water system, there's usually a source, okay? Because we don't live up in the mountains, our source is a water tower. There's a pump, okay? Next to every water tower, you guys ever notice the shape of a water tower? It's goofy, right? Most water towers look like a lollipop. What's with that? It's going to fall right over, right? I don't get it. Okay, in fact, even though the one we have by the school looks like a cylinder, inside, that's what the tank looks like. Really? Yeah, really. Why? I don't get it. Well, here's why. It's real simple. There's a pump inside that building. It's usually called the pump house. Big, like, barbed wire fence. I think it's a federal offense to actually tamper, right? Because, you know, water supplies and all that. So anyhow, pumps the water up to a higher potential. Bingo. Why is that important? Because how many of you guys go upstairs? You guys have an upstairs at home? Or maybe you're in a condo, apartment building, townhouse, whatever, right? So even if you're like on the 8th floor of a building, as long as there's what? Water above your head at a higher potential, a higher pressure, aha. When you open the sink, flush the toilet, you're okay. Make sense? So that's why water towers are shaped so weird. Because so even if it's like 90% empty, there's still water above your head. Okay? If it was just like a big old box down here, and then it's half empty, you won't be able to flush the toilet on the 2nd floor. That's gross. Okay? Got it? They've actually done interesting studies during like the Super Bowl, during halftime, how much the water pressure drops in the city. It's like how popular, you know, everyone's watching, how if the Bears are doing good, and, you know, during a pee break or what. Okay, too much information. Got it? Okay? So what are our two analogies? Water pressure and height on an electric hill. Electric potential. In volts is the amount of potential energy given per quantity of charge. 1 volt is 1 joule per 1 coulomb. Still kind of weird, right? Let's help you out here. Here we go. Next analogy. Let's talk batteries, okay? We're going to have 2 volunteers help us. AAA battery. How many volts? 1.5. Okay? What's this called? AA battery. How many volts? What? 1.5. What? I thought this was 1.5. Yeah. What a scam, right? What's this sucker called? C-cell. How many volts? 1.5. What? What are you small? Okay, yeah, 1.5. What's this guy called? D-cell. How many volts? What? 1.5. What's this guy called? 9 volt. How many volts? 9 volt. Whew. Okay, there we go. I don't get it. Okay, why? Okay, random? No, there's a method to the madness. Think about it. Where do you see these big batteries used, these D-cells, these big suckers? They're using things like what? Like flashlights, exactly. Especially like those cop flashlights, like the mag lights. Okay? I had a college job where I had to lock up this old building down in Champaign there, and they gave me like this big like mag flashlight. So I felt like a police officer running around. And you're supposed to actually carry it around your shoulder, so if you get jumped, you can whack someone on the head. But, you know, I think if someone was trying to rob the place, I'd be like, take whatever you want. Okay, anyhow. Okay, what else do you use D-cell batteries in besides like giant flashlights? Where else do you see these guys, okay? So in the old days, if you wanted to play music and you're like at the beach, you put these in a what? In a radio or boombox, right? Or in the 80s, when I was a kid, we called them ghetto blasters, right? And you got like your cardboard and you try to break dance and whatever, right? Okay, so anyway, why do we use these big batteries? Think about it, okay? If you have 4 of these in like a boombox, it's actually what? 1.5, 3, 4.5, 6 volts. So if you have 4 of these, you're running your circuit on a 6-volt circuit. The way you can think about that is like you're pumping up charges to the 6th floor of a building, and then the charges can flow and create electric pressure to run through that circuit. Okay? Contrast that to these little suckers. What do you see the AAA batteries use all the time? Like your calculator. That's a good example. In fact, get out your TI calculators and take a look. Okay, get out your TI calculators. How many batteries does your TI calculator run on? It runs on 4. 1.5 volts, right? 3, 4.5, 6 volts. So here's a question. I don't get it. 1.5, 1.5. Why? That's so annoying. They're different sizes. I don't get it. So here's why. Here's the difference, okay? Theoretically, let's say you go to the beach and your boombox dies and you're like, bummer, you can't play your beach tunes, right? The party can go on, even though you only have 4 of, let's say, these AA's, okay? All you got to do is you put these into the battery compartment, but they're not the same size. They'll slosh around, right? So a little trick. Anyone know the little trick? It's really old school. You take some aluminum foil from your picnic, you shove it between the battery terminals to connect them. Then you got 6 volts. So you can actually run your boombox off of 4 AA's instead of 4 D cells. Everyone's going to think you're some awesome MacGyver genius there, okay? But all it is you're trading off something. What are you trading off? You got the same voltage, the same height on an electric hill, but what's the downside? If I got 4 of these, I can probably run my beach tunes all day. But 4 of these, what do you think? Is it going to last all day? No, maybe like 2 hours or so. Enough to Get the party going. Get the grooves on, okay? Sorry, that was disturbing. Trying to keep you guys awake. You see that? Okay. So how about this? Opposite. Okay? Your calculator runs on 4 of these guys, right? Okay? You know our room's always a mess. It's like a disaster. There's junk all over the place. That's because we got this Science Olympiad team. They meet in here. This is their base of operations, and they're always working on building crazy stuff, like robots, catapults, whatever, right? So theoretically, nerd fest, big time, right? You could, if you want, actually, you know what? I'll even give you a bonus, extra credit if you want. Soup up your calculator. Yeah, trick it out. Super nerdy, okay? Trick up your battery to run off of 4 of these suckers. Yeah! 4 D cells, okay? Build a special battery box that attaches on. Yeah! Modify your calculator. There we go, okay? Street mod. So now your calculator runs off of 4 D cell batteries. It's still 6 volts, but what's the trade-off there? What's the advantage of running your calculator off the... Yeah, instead of changing your batteries like every 3 to 6 months, you could like have your calculator run for like 10 years. Yeah! Okay? The downside is your calculator would weigh like 4 pounds, right? You see that? So why do we have 1.5 volts? 1.5 volts. So annoying, right? 1.5 volts. 1.5 volts. Why? Answer's real simple. You want to build a device that can accomplish a certain job. So an engineer will design a circuit and pick the right size battery to match the job. Run a boombox, you need lots of energy for the whole day. Big batteries. Calculator, don't really need as much energy, and you want it lighter, so you pick a smaller battery. But it's not magic, okay? So how about this? Let's see if you really understand. Which battery has more energy in it? Which one has more energy? The big one. The big battery actually has more energy content. It has more charges in it, more chemicals, right? Can run devices for longer periods of time. However, which battery has a greater electric potential? Okay, same. If I said which one has the bigger voltage, now you understand. 1.5 volts. Potential, electric potential, is commonly called voltage because it's measured in volts. That's what you understand. In the end, all you care about is give me the juice. I need the juice to run your devices. You see that? So volts is named after this Italian scientist named Alessandro Volta, who discovered things we know about electric current, developed the first battery. So in honor of him, we name it volts. Okay? So in real life, you care about volts. It's all about the juice to run your devices. One last analogy to help you understand, okay? This one's actually really good, but it involves some power lifting with these bricks. So I'm going to need 2 volunteers. Here we go. Electric potential. You're not used to that, but you are used to voltage, right? When you change your battery. Don't confuse the idea of energy and energy per charge, okay? A AA, AAA, C cell, and D cell are all 1.5 volts, but they're not the same thing. Obviously, a D cell battery is a lot bigger. It's got a lot more energy. That's like our lead brick, right? A 9-volt battery lifts a charge to a much higher potential, right? But it doesn't have quite as much energy, but it's for a different purpose. It creates a greater pressure is the way to think of it. If I drop the foam brick off the top of the school and hit someone on the head, they're okay, right? It's at a high potential. But if I drop the lead brick, that's bad. That would be a homicide thing. I would never do that. Got it? Don't confuse the idea of energy and energy potential, electric potential. Big idea, easy to confuse, but if you focus on the definition and use analogies, it actually makes a whole lot of sense. There you have it. Electric